To do design calculations for evaporators, we need to write down the mass and energy balances. I recommend that you watch this video with a friend so you can help each other. Try to do the following 3 steps. Look carefully where I draw the system boundary and count only flows that pass across the system boundary when making mass and energy balances. Step 1. Write mass balances. A. Steam side of heat exchanger, that will be 1 mass balance. B. Feed side of heat exchanger, that will be 2 mass balances. Step 2. Write the energy balance for the entire system, excluding the condenser. And step 3. Write down the heat transfer equation for the heat exchanger, that is, the heat being transferred across the wall that divides the heat exchanger into 2 parts. That's also kind of energy balance. Use the following symbols. The flows are S, K, F, L, and V in kilogram per second. XF and XL are the weight fraction of solids in F and L. The enthalpies are HS, HK, HF, HL, and HV in kilojoule per kilogram, using capital H for vapors and lowercase h for liquids. Pause here and try to write down these 5 equations, assuming steady state, that is, in equals out. The steam side is pretty simple, as we only have 1 component. S goes in and K goes out, so S equals K. On the feed side, we have 2 components, the volatile liquid and the solids. The liquid comes in as F and goes out as L and V, so F equals L plus V. For the solids, we have F times XF as solids flowing into the systems. If the phase separation is perfect, there is no solids in the vapor, so what comes out is L times XL. In a real evaporator, we might need to include V times XV, because some liquids might be entrained in the vapor, that is, some liquid follows the vapor out as small liquid droplets. We can also have a situation where the solids have a low but still significant volatility. So what about the energy balance? We have a flow S coming in with an enthalpy of HS and a flow F with an enthalpy HF. Thus, what comes in must be S times HS plus F times HF. Similarly, what comes out must be K times HK plus L times HL plus V times HV. Remembering that S equals K, we can reshuffle this equation to also tell us the energy Q transferred from the steam. So Q equals S times HS minus HK equals V times HV plus L times HL minus F times HF. This energy Q transferred from the steam can also be expressed using the heat transfer equation for heat exchanger. So Q equals S times HS minus HK, which equals K times A times TS minus T. As we mentioned in the previous video, the true temperature difference is actually not Ts minus T. So when we use the simplified temperature difference Ts minus T, we need to use the so-called apparent overall heat transfer coefficient. What this means is that we have shifted from a problem in describing complicated variations in temperature difference and overall heat transfer coefficients along the heat exchanger to simplified temperature difference and an apparent overall heat transfer coefficient that is rather difficult to estimate. In this course, however, we will typically either give you the value for the apparent overall heat transfer coefficient, or give you all other information you need so you can calculate it. Note that there is an implicit assumption hidden in the 2 last equations in the energy balances. We assume that all heat that is provided by the condensing steam is transferred to the cold side. That is, we assume that there are no heat losses.